Hello and welcome back to Real Analysis. And of course, as always, I want to thank all the nice people who support this channel on Steady, via PayPal or by other means. And there, please don't forget, on Steady you can download the PDF versions and quizzes for the videos. Okay, and now in part 62 we will talk about the integral criterion for series. For this, please recall that we have already introduced the notion of an improper Riemann integral that could, for example, go from 0 to infinity. In fact, in this case, we immediately see the connection to a series of numbers. For example, in the last video we have shown that the comparison test also works for improper Riemann integrals. Moreover, now we will show that we can use an integral to show that a series is convergent. Indeed, this could be helpful because for integrals we have the fundamental theorem of calculus. This means that it could be much easier to calculate a particular integral than a series. However, for having the convergence of a series, it's sufficient to have the convergence of a suitable integral. So maybe this is not hard to see, so assume that this area we have here on the left hand side is finite. Then, when we have a series below this graph here, then the area of the rectangles should also be finite. In other words, the series then has to converge. Okay, then I would say, let's formulate this statement now. So this is a theorem often called the integral test for convergence. Now what we need is a function f with domain given by the interval 0 to infinity, which is also non-negative. So we could write that the codomain is also the interval from 0 to infinity. However, what we also need, as you can see in the picture, is that the function is monotonically decreasing. Okay, that is all we need, and then we can conclude that the series from k is equal to 0 to infinity of f of k is convergent if and only if the improper Riemann integral is convergent. Hence, if we know that this integral gives us a finite number, then the series also gives us a finite number, and vice versa. And moreover, in this case, we can estimate the values. First, we see that the series is always larger than the integral. Therefore, the difference is greater or equal than 0. And maybe this is something we can explain in a picture. Now, if this is the graph of the function f, the series is evaluated at the integers at the x-axis. For example, f of 0 would be this value, f of 1 has this value, and so on. Now, adding up all these values is the same as adding up the areas of rectangles because the width is 1. Then the important thing you should see is the area is larger than the integral. So you see, this immediately explains the implication from the left to the right. And also this inequality here. Now, in order to explain the other implication, we have to look at the picture again. Of course, we still have the same values here, but now we have another idea. Instead of drawing the rectangles to the right, we could draw them to the left. Then the first one, for f of 0, would lie outside the area of the integral, but this is no problem at all. It's a finite number, which means we could ignore it, and this means that we start the series at k is equal to 1. Hence, then we see that all the other rectangles lie inside the integral area. In other words, the sum of all the rectangles is less than the integral of f. And there we see, there we have the other implication. Hence, if this integral is convergent, then the series starting with 1 is also convergent. However, then the series starting with 0 is of course also convergent. Moreover, from this we can conclude that the difference here cannot be larger than the first entry. In other words, the value of f at 0. Okay, and with this, the formulation of the theorem is finished. And in some sense, as you can see, we already explained the proof of it. However, I would say, let's do it again in the formal correct way. Still, it's a good thing that we already have the ideas we need. For example, we know that f is monotonically decreasing. From this we can conclude that for all k greater than 1, we have that f of k is less or equal than f of k minus 1. Moreover, all other points x between k minus 1 and k also fulfill this inequality. So we immediately get this from the monotonicity. And now we know that the integral conserves such a monotonicity. Therefore, we can put an integral sign on all sides of the inequalities. However, now of course we only integrate from k minus 1 to k. There, please recall, x needed to be in point from this interval. So in summary, the monotonicity of the function f gives us immediately these nice inequalities for the integrals. Also, you should see here on the left hand side we have picked a rectangle here, and here on the right hand side we have picked a rectangle there. In other words, this is simply the value f of k, and on the other side we have the value f of k minus 1. Therefore, in the next step we can sum up all the rectangles. Of course, when we start with 1 and go to n, we don't change the inequalities. Indeed, now we see the inequalities of the pictures again. In the middle we have the area given by the integral, and on the left and the right hand side we have the rectangles summed up. Therefore I would say, let's formulate this in a nicer way. First, the middle part here we can write as the integral from 0 to n. And for the right hand side we can write f of k, and then we start at 0 and go to n minus 1. And then you should see we have everything we want. Namely, when n goes to infinity and this here gives us a finite value, then this is also a finite value. On the other hand, if we send n to infinity here on the right hand side and this series gives us a finite number, then this integral in the limit also exists. Therefore, we could say, while considering these limits n to infinity, the first part is shown. Then the second part was the inequality, and this comes also out. More precisely, if the limit exists, we have these two inequalities, where on the left hand side we have the series starting at 1, and on the right hand side the series starting at 0. Hence, by subtracting the series here, we get the two estimates from the theorem. So in summary, everything is formally proven now. So you see, the proof was not so hard, but the statement is something you really should remember. Therefore, I think it's a good idea to look at an important example. In fact, this one you really should remember. Here we look at a series that starts with k is equal to 1. This means that the corresponding integral should also start at 1. Of course, it's no problem at all to adapt the theorem to this case. And now the series we consider is 1 over k to the power alpha. And now depending on the value of alpha, we get two cases. Namely, we get a convergent series when alpha is large enough, which means alpha should be greater than 1. And on the other hand, if alpha is less or equal than 1, the series is not convergent. Of course, if you want, you can assume that alpha is positive. Simply because if alpha is negative, it's very clear that the series can't be convergent. Okay, now this statement here we can prove by using an improper Riemann integral. And of course, the function in the integral should be 1 over x to the power alpha. And there you see, the good thing for this integral here is, where we integrate from 1 to b, that we know an antiderivative for the function. More precisely, we have to distinguish two cases. Now, if alpha is not 1, the antiderivative can be written as the function x to the power minus alpha plus 1. Because now the derivative of this function gives us x to the power minus alpha, which is 1 over x to the power alpha. Therefore, you see, we only have to fix the constant, the factor that comes in front. Obviously, this is also minus alpha plus 1, but I write it as 1 minus alpha. And there you see, this whole thing does not work for the case alpha is equal to 1. However, there we only need to know the antiderivative of 1 over x, which is, as you might know, the natural logarithm. Okay, and now both antiderivatives are evaluated at b and 1. Okay, then let's do it and put in b and 1, but then I want to distinguish the first case with alpha is greater 1 and alpha is less than 1. Okay, of course it's not so complicated, we put in b and then we subtract putting in 1. However, now I want to make it clear that this power is negative. So when I put parentheses here, we have a minus sign here. Okay, now moreover, for the second case we have the same result, of course, but now the power is positive. So let's make this clear by putting 1 in the front. So we subtract something that is always less than 1, therefore the power is always positive. Okay, then in the last case you see, we just have log of b. And now the question we should answer is what happens when we send b to infinity? Now in the first case, because we have a negative power, this one vanishes and only this term remains. Most importantly, we get out a finite value. However, this does not happen in the second case because the power here is positive. Hence, the whole thing diverges to infinity. And we have the same as you know when we consider the logarithm. Therefore, now the theorem tells us that we have convergence only in the case that alpha is greater than 1. Okay, there we have it. Now you know how we can combine improper Riemann integrals and series. And in the next video we will continue with the improper Riemann integrals. So I hope that I see you there. Have a nice day and bye.